Hayashi from Tokai University is going to talk about 5 brane webs and 5D n equal to 1 rank 2 theories.
Okay. Thank you very much for the organizers to give me this opportunity to speak here. And today I'm going to talk about some aspects of 5-dimensional gauge theory and 5-brane web diagrams. And I'm going to propose some new types of 5-brane web diagrams that realize some exceptional rank 2 gauge theories. And this work is based on the collaboration with Sonsu Kim and Kim Yori and Futoshi Yagi. So the main topic of this talk is 5-dimensional gauge theories with 8 supercharges. And I'm going to make use of 5-brane web diagrams to realize those 5-dimensional gauge theories. Well, one of the advantages of using that kind of 5-brane web diagram is that we can see some non-perturbative effectively explicitly, so we can see the dualities among various 5-dimensional gauge theories, and also we can compute the Nicholas partition function by applying the topological vertex. So the 5-brane web diagrams are very useful to study the 5-dimensional gauge theories, but the question is what kind of gauge theory we can realize by using 5-brane webs. Well, so if we put n parallel D 5 branes on top of each other, we can realize SU and gauge group. And if we introduce some orient for the 5 brane, we can realize a USB2 and gauge group or ISO and gauge group. Then the question is, can we construct some exceptional gauge groups by using these 5-brane web diagrams? Well, in the FCL conference last year, I proposed some new types of wave-like description for the pure E6, E7, E8 gauge theory, where that actually goes beyond the standard wave diagrams because the wave diagram, well, wave-like configuration is written by using a special type of gluing. So I'm now interested in realizing whether we can have the other exceptional gauge group like F or G2. And in this talk, I'm going to propose a 5-brane web diagram that realizes the pure G2 gauge theory. And in fact, I'm going to propose 2 types of 5-brane web diagrams that realize the pure G2 gauge theory. Well, very surprisingly, sort of standard 5-brane web diagrams written on a plane actually realize this exceptional G2 gauge group, where we can just introduce an orient for the 5-brane. And it is also straightforward to introduce the flavors to this pure G2 gauge theory, but I will not talk about this in this talk because the time is limited. But instead, I'm going to talk about some application by using these 5-brane web diagrams of pure G2 gauge theory. And one application is an interesting duality involving this G2 gauge group. So from a geometric construction by using M-theory computation on Calabria's 3-fold, in fact, this pure G2 gauge group, pure G2 gauge theory in 5 dimensions is dual to an SU3 gauge theory with chance times level 7. In fact, this kind of duality can be also seen from the brane configuration that we will realize. And the other application is we can also compute the Nicholas partition function of the pure G2 gauge theory. And in fact, in this Nicholas partition computation, we will also see an interesting relation between this pure G2 and also pure SU4. So this is a plan of the talk, and I'm going to first review how we can construct the 5-dimensional gauge theories from 5-brane web diagrams, and then move on to one type of construction for the pure G2 gauge theory. And this first type of construction can be useful to understand the duality between pure G2 and SU3 with chance level 7. And now, and then move on to the second construction of G2, and this is now useful to compute the Nicholas partition function. So let me first review the basics of the construction of 5D gauge theory by using a 5-brane web diagram. So we are going to construct a 5-dimensional gauge theory with 8 supercharges as a valid volume theory on a 5-brane web diagram. So a 5-brane web diagram is kind of a configuration which consists of various types of 5 branes, like D5 brane and NS5 brane, and also a PQ5 brane. And PQ5 brane is kind of a bound state of PD5 and QNS5 brane. And we also introduce an orient for the 5 brane. And this is, sorry. this is a configuration. So the configuration of the D5 and S5 and PQ5 and orient for 5' is summarized in this table. So D5 and orient for 5' extend in the same direction from this 0 to 5. And S5' extend from 0 to 4 and also this x6 direction. And PQ5' extend from 0 to 4, and it is some line in this two-dimensional plane with a particular slope. So this 5-dimensional part here is a 5-dimensional space-time of 5-dimensional gauge theories. And 5' D5 and S5 or PQ5' and also 5' is some line in this two-dimensional plane. And basically the structure of the combination of the lines here determines what is the gauge group and also the matter content of the 5-dimensional gauge theory. And since a non-trivial structure only appears in this two-dimensional plane, I'm going to write only this part to represent the 5' wave diagram. So let's think about a simple example. So this is a wave diagram for pure SU2 gauge theory with zero discrete angle. So I chose the horizontal direction as x5 direction and vertical direction is x6 direction. So a horizontal line here represents a D5 line and vertical line is an NS5 line. So since we have these two D5 lines that are parallel to each other, so this diagram represents some SU2 gauge theory. And when D5 line meets an NS5 line, due to the charge conservation, we will have this 115 line, which is kind of one set of D5 and S5, and also 1-15 line here. And PQ5 line in general is represented by a line with slope Q of P. And it is straightforward to increase the rank. So now this is a wave diagram for pure SU3 gauge theory with zero chance and level. So now we have 3 color D5 lines, and we have some string that connecting these three color D5 lines that give rise to a double boson with SU3. And these 3 color D5 lines are connected by other PQ5 line, which respects the charge conservation. So this is some basics of the construction for usual SUN gauge theory. Now if we introduce our orient for the 5' it is also possible to realize the other gauge group like USB2N and SON gauge group. So for example, if we put in D5 lines on an O5 plus or O5 tilde plus, then the gauge group will be USB2N. And if we put in D5 on O5 minus, we have SO2N. And if we put in D5 on O5 tilde minus, we will have SO gauge group. I'm going to write one example by using this orient fault. And this is a wave diagram for the pure SO7 gauge theory. So we have 3 color D5 lines on top of an O tilde minus plane. So 3 color D5 line on top of an O tilde minus plane give rise to SO7 gauge group. So this is some basics of the construction for 5-dimensional gauge theory by using a 5' wave diagram, including an orient for the 5'. So now let's try to construct a G2 gauge theory by using this 5' wave diagram. And to construct the G2 gauge theory from the 5' wave diagram, the crucial point is by using a Higgs mechanism. So the pure G2 gauge theory can be realized by Higgsing SO7 gauge theory with a hypermultiplet in the spinel representation. So starting from the SO7 gauge theory with a hypermultiplet in the spinel representation, if we tune the Coulomb branch modular and also the mass parameter of the spinel, then a Higgs branch opens up, and on the Higgs phase, if we go to a far infrared limit, then on the Higgs phase, the Lorentz effective field theory becomes the pure G2 gauge theory. So the question is whether we can realize this Higgs mechanism in terms of the 5' wave diagram. So to realize this Higgs mechanism in terms of 5' wave diagrams, basically we need to carry out these 2 steps. So the first one is first we need to construct a 5' wave diagram that realizes SO7 gauge theory with a hypermultiplet in the spinel representation. And second, we need to further Higgs this 5' wave diagram. And if we are able to carry out these 2 steps, then the resulting 5' wave diagram should be the one for the pure G2 gauge theory. Well, these 2 steps themselves are a bit non-trivial. For example, it is not so straightforward to introduce the spinal penetration in the brain configuration. But actually, the recent progress of the 5' wave diagram, these two steps are actually possible. So we are able to write down our 5' wave diagram for the pure G2 case. So let's see these two steps one by one. So first, let's try to introduce a spinner matter in SO7 gauge theory. So this was the wave diagram for the pure SO7 gauge theory. So we have 3 color D5 lanes on top of one O5 children minus. And in fact, introducing a spinner matter is very actually simple. So the claim is that if we introduce this 115 lane here, then this diagram actually gives rise to the SO7 gauge theory with spinner matter. And the claim is that, in fact, the hypermultiplet in the spinal penetration is realized non-perturbatively in this diagram as an USB0 instant. So introducing this 115 lane may look a bit trivial, and this may look like introducing basically nothing, but actually it's not true, because there can be some string junction which connects this 115 lane to some 5 lanes on this SO7 part. So that may look like kind of an SP0 instantons, and by the argument of the instanton computation of SP and also the Hicksing, these fields coming from the string junction will be in the spinal penetration of SO7. So this diagram actually looks realize SO7 gauge theory with the spinner matter, and also the spinner flavor symmetry of this one spinner, which is SU2 gauge. This SU2 flavor symmetry is seen from this parallel 1-1 external 5 lanes. So if this 1-1 external 5 lanes are top on each other, then we have SU2 flavor symmetry. So in other words, the distance between this 115 lane and this 115 lane is related to the mass parameter of the spinner hypermultiplet. So next question is basically how we can Higgs this diagram. So in order to open up a Higgs branch, we need to tune the mass of the spinner matter to be 0. So basically we need to put this 115 lane and this 115 lane on top of each other. Well, this is again a bit non-trivial because there is some part involving an orient-fold plane. So it may look like that it is a bit difficult to put these two 115 lane on top of each other. But actually, it turns out that we can perform a kind of flop transition for the plane configuration with an orient-fold 5 plane. And the flop transition is something like this one. So we have some 5 lane configuration with an O5 plane. And if we put these two 5 lanes close together, and in fact we can go further and we will get this kind of configuration. So if you apply this kind of transition to here, you will get this kind of wave diagram. Then by performing the standard flop transition, we can move this 115 lane and this 1 external 5 lane close together. So let's, for example, perform the flop transition here. Then we will get this diagram. Then we further perform a flop transition here. We will get this diagram. And from this diagram, now we can tune this length and also this length. Then we can put these two 1 external 5 lanes on top of each other. And if we put these two 5 lanes put on each other, then a Higgs branch should open up. And to see that kind of Higgs branch, it is useful to introduce 115 lane at the end of this 1 external 7 lane at the end of this 1 external 5 lane. So if we put this 7 lane at the end of this 1 external 5 lane, and after tuning this one, these 115 lane becomes coincident, then there is another Higgs branch appears, which is basically given by a motion of the piece of 5 lane within this 7 lane. I don't know what is the variety of this one, but this is some one-dimensional space. Maybe, yeah, okay. It is SU2 flavor symmetry and one dimension, so probably that's correct. So this is the Higgs branch of this SO7 gauge theory with one spinner matter. And to go to infrared limit of this Higgs phase, it's effectively realized by moving this one, this motion of this piece of 5 lane to infinity far away. And we will basically arrive at this kind of conclusion. And we claim that this is a web diagram for the pure G2 gauge theory. So somehow the web diagram for the pure G2 gauge theory is kind of a standard web diagram with just orient fold 5 prime. So we can use this web diagram for the pure G2 gauge theory to think about the duality which is proposed by using a geometric construction. So the duality is something like this one. So pure G2 gauge theory is dual to pure SU3 gauge theory with 7 Chern-Simons level. So this was a 5 web diagram for the pure G2 gauge theory. And the duality between this pure G2 and SU3 Chern-Simons level 7 will be understood as S duality in this case. So if we perform S duality, which is essentially a 90-degree rotation of this diagram. So if we perform 90-degree rotation, we have this 3-color disequilibrium, which is not on top of an orient fold. So this web diagram looks like an SU3 gauge theory, and the question is what is the Chern-Simons level of this SU3 gauge group? Well, I mean, Chern-Simons level dependence will appear in the effective prepotential. So for example, if we can compute the effective prepotential by using the 5-lane web diagram of the pure G2, we can see what is the Chern-Simons level of this SU3 gauge theory. Well, similarly, if we are able to compute the tension of the monopole string, we can also understand the Chern-Simons level because the tension of monopole string is given by a derivative of the effective potential with respect to the Coulomb branch moduli, which also depends on the Chern-Simons level. And in terms of 5-lane web diagram, the monopole string is realized by the disequilibrium spanning a face of the web diagram. So the tension of the monopole string is basically the area of a face of a diagram. That is basically, okay, thank you, easy to compute. So if we compute the area of the face of the diagram of the previous diagram, it is, we can confirm that the 5-lane wave diagram will write SU3 gauge theory with 7, Chern-Simons level 7. Well, actually, this has another interesting implication. So this is a wave diagram of SU3 gauge theory with Chern-Simons level 5. And this is a wave diagram for SU3 gauge theory with Chern-Simons 7. So the difference between these two 5-lane wave diagrams is that we replace this part with an ON plane. So by replacing this part with an ON plane, then Chern-Simons level increase by 2. So from this conclusion, one can naturally guess that we can also replace this part by an ON same plane, and which will increase the Chern-Simons level by 2. And this is indeed true. So if we consider this kind of wave diagram, and again we can compute the tension monopole string by computing the area, it is possible to confirm that this wave diagram represents SU3 gauge theory with Chern-Simons level 9. And this SU3 Chern-Simons level 9 theory can be also constructed from the geometry by using serial computation Caravia threefold. But now 5-lane wave diagrams also realize basically all the SU3 gauge theory with any Chern-Simons level, which is predicted from the effective prepotential. Okay, so this is one construction for 5-lane wave diagram or for the pure G2 gauge theory. And there is actually another way to realize the pure G2 gauge theory. So let's see what we have done so far. So we used SO7 gauge theory with one spinor matter. And if we fix this one spinor, then we get pure G2 gauge theory. And in fact, SO7 itself can be realized by fixing of SO8 plus 1 vector. So what we have done actually can be sort of two fixing starting from SO8 plus 1 vector and one spinor. Well, here there is some interesting thing about SO8 gauge theory. In fact, SO8 gauge theory has a triarity which exchange a vector matter and spinor matter at the conjugate spinor. So SO8 with one vector and one spinor is in fact equivalent to the SO8 gauge theory with one spinor and one conjugate spinor. So since these two SO8 gauge theories are equivalent, if we perform the same fixing, then we should get pure G2 gauge theory. And what is interesting is that the wave configuration for SO8 plus 1 vector and 1 spinor and that of SO8 plus 1 spinor and 1 conjugate spinor are quite different. So even if we perform the same fixing, and we should get the same pure G2 gauge theory, but the wave diagram is kind of very different from the one we constructed before. So basically, basically, I mean, how we carry out this kind of operation is same as before. So we need to introduce the one spinner, one conjugate spinner, and fix this. And for that, we basically use the flop transition. And then the result of the five-line wave concretion is something like this. So now five-line wave diagram is written just with an orient for the five-line. And one thing that is interesting from this five-line wave diagram is that, for example, we can write this part as a mirror image. Then the diagram looks like this one. So this was originally in this upper plane, but we can use a mirror image like this one. Then this is essentially the wave diagram for pure SO4. And the difference is this color D5 plane is stuck at orient for 5 plane. And actually, this difference is not at the level of this 5 plane wave diagram, but actually, the Nicholas partition function of pure G2 gauge theory is very similar to the one for the pure SO4. So let's see how the Nicholas partition function of G2 can be computed from this wave diagram. So we will basically apply the topological vertex to the wave diagram, which computes the Nicholas partition function. And recently, the formalism is extended to the wave diagram, including an orient for the pi plane, and the method basically makes use of the mirror image with a careful assignment of Young diagrams and framing factors. So if we want to apply this topological vertex to this wave diagram, we will make use of the mirror image like this one. So if we use this mirror image, then this wave diagram is almost the same as SU4 gauge theory, SU4 wave diagram. So there is basically no problem to apply the topological vertex. So if you apply this topological vertex, actually one subtlety comes from the Young diagram assignment for the 5 plane, which is on this O5 minus. So only the difference from the pure SU4 case is basically this part is transposed. Okay. And in terms of the some schematic form, so this is a result of the topological vertex computation. And the difference from the one for the pure SU4 is we have this sign factor associated with this third Young diagram. And this power is -1 for the pure SU4, but this is 1. And this part is transposed. But this is the only difference between pure SU4 and the pure G2. And indeed, if we compute this partition function, we have found that the computation, well, result of this partition function agrees with the partition function of pure G2 until the two-instant order. So let me conclude. So we constructed two types of 5-plane wave diagrams for pure G2 gauge theory. And very interestingly and surprisingly, the wave diagram is a sort of standard 5-plane wave diagram, just with an orient for 5-plane. And that kind of wave diagram can be also used to see the duality between pure G2 and SU3 with chance size level 7. And we can also compute the Nicholas partition function of pure G2 and found some interesting relation between pure G2 and SU4. Well, I need not talk about the addition of the flavors in G2, but it's very straightforward to compute the partition function. It is very straightforward to add the flavor to the G2 gauge theory, and we can, for example, compute the cross partition function of the G2 gauge theory with some flavors. And recently, by using some 6-dimensional genus, there is another computation for the cross partition function of G2 with flavors. So it will be interesting to compare our result with the results computed by different methods. And including the flavors, there are also some interesting duality involving G2. So for example, G2 with 6 flavor is dual to SP2 plus 2 antisymmetric and 4 fundamental. And that is also dual to SU3 with 4 chance and level 4 and 6 flavors. And that kind of duality can be also seen by using the 5-plane wave diagrams. Okay, thank you.
Thank you very much. Questions? We have plenty of time.
At some point, you had the realization for SU3 with Chen-Simons equal 9. Mm-hmm. And what's the S dual of that? You could flip it again back.
Yeah, we can consider S dual of that SU3 with Chen-Simons level 9. But then we have two orient for the 5-plane. And that is, we have some periodic direction in the vertical direction, which means that that theory has a 60 uplift.
Good. That's interesting. Okay. And what is the uplift?
Well, we don't know. We don't know what is the 60 UV compression of that.
Thanks.
We saw that the orientifold plane changes whenever it crosses the PQ brane. Do you have rules on how it changes?
Yeah, so basically if the orientifold cross NS5 brane, then O5 minus goes to O5 plus, or O5 plus goes to O5 minus. This is basically the rule. And also in this case, we need to be careful with the D5 brane charges. So O5 minus and O5 plus, the difference of the D5 brane charge is 2. So we also need to be careful with the discharge conservation if we write down configuration of PQ5 brane with orientifold 5.
More questions? Comments? If not, let's thank you. Up. Yep.
Sorry, could you quickly summarize again how you were able to compute the Nekrasov partition function for this theory?
Well, so basically the topological vertex computation is, so originally, so this diagram is the one for the pure G2 gauge theory, and we will make use of, so applying directly to the wave diagram is a bit difficult because we don't know how to do it, but we can use a mirror image of this one, and then we go to this one. In this case, basically we decompose these wave diagrams into the vertices and lines, and each vertex we assign a topological vertex and basically some of the diagrams.
Okay, we thank Hirotaka again. And we come back at 4.